Let's talk. Same thing for this topic.
We want to clear up from last class before going on. The first thing is this silly issue about signs. It's not going to be very illuminating since we confused ourselves about the signs of the action in last class. Let's clear that up. Okay, so the first question we should ask is, how do you know what is the correct sign? Yeah, how do you know what is the correct sign of the action? Just starting with the first action, which by the way has a name, it's called the number root action. So remember we said that the action was equal to minus 1 by 4 pi, or 2 pi alpha prime, times determinant, square root of minus del alpha x mu del alpha x mu. That was the action. Okay, so just to convince you that this is the right physical sign for the action, let's do the following. Let's take a configuration of this string that stretches infinitely long in the x1 direction. Okay, so we've got a string whose base string configuration is stretching infinitely long in the x1 direction, so the origin in all other spatial directions. Okay, and for this string, let's be completely physical. Let's use a gauge such that x1 of sigma is equal to x1 and tau is equal to x0. And let's look at what this action becomes in this stage. Okay, we're only using this for interpretation purposes here. So we'll also confine ourselves to an action for small fluctuations around this equilibrium configuration. So we'll confine ourselves to an action that is quadratic in fluctuations. Okay, and let's see what this becomes. Useful exercise to make contact with something. Okay, so what do we get? Well, so first let's write out this stuff in more detail. So this s is equal to minus 1 by 2 pi alpha prime, and then there's integral, and then this fancy determinant, as we saw last time, could be written as minus x mu dot times x mu prime prime, and then plus x mu dot times x mu prime for this. Okay, this is minus and this is plus, this is minus. Fine. Now I want to take this action and expand it to quadratic order in fluctuations. So the first question I ask is there any term in this action that's not zero? At zero order fluctuations. Is there a background piece of this action? And clearly there is, because x mu dot x mu dot is not zero, because it gets contributions from x0. So that part is minus 1 because of the negative metric in the time direction. The space, the time direction of space. And x mu prime is not zero from the contribution in the x1 direction. So that part is plus 1. Okay, so we see that to zeroth order, the action evaluates to integral square root of 1. Great. Now let's deal with fluctuations. This term is 0 in the background. Okay, and okay, so this term is 0. Okay, we should do this carefully. We should do it carefully, but let me just take what comes from this term to save time, to get some addition. What bother us very much. So very quickly, if we want to do what comes from this term, we'd have to take background here and fluctuation here, or background here and fluctuation here. So background here and fluctuation here gives us minus x mu dot x mu dot. Okay, so now first is mu. This mu should become I. You see, because of these d degrees of freedom, 2 have been cage fixed, so they're not dynamic degrees of freedom. Okay, so it's only the remaining d minus 2 that are dynamic degrees of freedom. So the part where mu runs over either 0, the time coordinate, or 1d, coordinate where we gauge phase only contributes to the background. There are no fluctuations in those directions. Is this clear? Okay, so suppose we were doing the rewriting exactly. We should hurry up. But suppose we were doing the rewriting exactly. Actually, this still won't even contribute to quadratic order for this reason. So suppose we were doing the rewriting exactly, what would this thing become? So this thing would become -1 plus x mu xi dot xi dot. Okay, this term would become 1 plus xi prime xi prime. And this term would become plus xi dot xi prime. So this is an exact rewriting of the expression above, making no assumptions. Okay? Now you see that this thing is quadratics. We don't even need to. To quadratic order, we can forget about it. To quadratic order, what do we get? We get 1 by 2 pi alpha prime. Then because we're doing quadratic order, we get a half from the square root. And we get integral of, and there was a minus sign here, from this minus sign. So we get integral of 1 minus xi dot plus xi prime xi. If I've written the square root, 2, which is equal to 1 by 4 pi alpha prime into integral of 2. And I'm drawing my minuses, and this is now minus xi dot plus xi prime xi. Is this clear? Okay? So now we know the constant term of the action, who cares about it? Though we might, just for future purposes, let's remember that it's a negative constant term. Okay? So this is 1 by 2 pi alpha prime minus plus 1 by 4 pi alpha prime into xi dot squared minus xi prime. Now this you see is a physical action. Because this gives you physical action because it has positive kinetic. Okay? So it gives you a physical action for fluctuations of the string. In a condensed matter, of course, if you write down an action for fluctuations of a string, you would write down this action with some phenomenological tension. Okay? So that determines the sign of what we started with. That better have been minus. Okay. Now, we saw that last time that we got the same, this was equivalent classically to 1 by 4 pi alpha prime with a plus or minus, which there was a point where we took the square root. We weren't sure which sign to take. 1 by 4 pi alpha prime square root minus g alpha beta del alpha x mu del alpha x. Okay. Which sign should we be taking? Well, there are two arguments, both of which we did the same answer if you did them carefully. Though one of them was, I was doing it confusely last time, getting the wrong answer. The first argument is whether we better have the kinetic term positive for the physical fluctuations. Now, the physical fluctuations are the I fluctuations. So they have no sign from the space-time metric. Okay? But the kinetic term does have a sign from the world sheet metric. Does have a minus from the world sheet metric. Okay? So if we want to make it positive, this had better be the negative sign. Is this clear? What I was getting confused about was the positive definiteness of this action last time. That was stupid confusion. As we can see. Okay, let's take the same configuration as before and check that on the background this thing evaluates to something negative. Okay? So the configuration we're looking at is that x0 is equal to tau and x prime is equal to sigma, some constant. X1 is equal to sigma. Okay? Now let's see. You see, the x1 part is clearly positive because both signs are positive. But the x0 part is also positive because both signs are negative. So in here you get something positive and then there's a minus sign which agrees with this minus sign. In fact, value will also be because you get 2 which cancels out. Is this clear? Okay, so from any point of view, it falls through correct. Last time I was remembering the minus sign in the world sheet of metric, but forgetting the minus sign for x0 in space time. Okay, so this is the right sign when in the process, in the derivation, when we do the square root, we should take it this. Any questions about it? Okay, great. So that was clearing up point number 1. Now we want to go back to our quantizations. Okay. So we want to go back to our quantization of the string. Let me remind you of what we saw last time. We decided to do the quantization. We decided to do the quantization in this Polyakov, the so-called Polyakov action. So we decided to work with 1 by 4 pi alpha prime with minus square root minus g integral of d alpha beta del alpha x mu del okay. Then we fixed gauge. We gauge fixed. Remember, this action was classically equivalent to the early action only when both diffeomorphisms as well as Weyl transformations were treated as gauge index. Now we fixed gauge to set g alpha beta equals eta. The flat Minkowski metric of the world sheet. Very good. But we realized that this gauge fixing procedure did not completely fix gauge. Okay? There were defining sigma plus and sigma minus. Sigma plus is tau plus sigma. Sigma minus is equal to tau minus sigma. Okay? There were gauge transformations that were not fixed, which were of the form sigma plus is equal to f of sigma plus tilde, for instance, and sigma minus is equal to g of sigma minus tilde. Okay? Now this looks like a very small amount of gauge ambiguity, because this functions 1 variable around 2. But it's precisely the sort of gauge ambiguity that is relevant to classical, that is important to classical physics. Okay. And why is that? That's because we saw that solutions to the equations of motion, the classical solutions to the equations of motion, had all the x's being a function of sigma plus is a function of sigma minus. Okay? So, naively it appeared as if we had 26 functions of sigma plus, d functions of sigma plus, and d functions of sigma minus. Now, those d functions were each constrained to obey a constraint equation, which I'll remind you of in a moment. So that looked like it went to d minus 1. However, this reparametrization invariance actually tells you that it's d minus 2 functions of sigma plus and d minus 2 functions of sigma minus that parameterize inequivalent solutions. Okay? That was an important crucial point. So the space of classical solutions was space of d minus 2 functions of sigma plus, d minus 2 functions of sigma minus. Okay. Now, what do we do? Last time what we did was, in order to fix this ambiguity, we took one of the functions, which we chose to be x minus, okay, and set all the non-zero mode parts of it to be 0 by this coordinate redefinition period. Because of the periodicity of the sigma coordinate, we couldn't touch the 0 mode parts. You couldn't redefine them away, because that would break periodicity. So this was alpha prime p minus tau, and then something I forgot to write last time. So there's a center of mass. That's always there. Just a constant. So we were able to use our gauge redundancy to set this thing to this form. Okay? That made it manifest that once we're in this gauge, it's manifest that there are d minus 2 difference. There are d minus 1 left after we set this gauge, and then this constraint. Okay. Now the question is, how do we take this classical phase space, this classical space of solutions, and quantize it? Okay? Can you find a reasonable procedure that will allow you to take this classical physics that we've solved completely and to convert it into quantitative? Okay? So in order to do that, I'm going to give you a 5 or 10 minute introduction, to a way of thinking of quantization that is possibly broader and more, we make very limited use of it, but it's possibly broader than ways you have been introduced to before. Actually, people who took my quantum mechanics 1 class, we use this method to quantize Landau levels. But I don't think you remember that. Okay, so this method has a fancy name. It's called geometric quantization. So we will use such a small part of it that we won't require much names, terminologies, anything like that. But let's just see the method. You see, how do we normally do quantization? What we normally do is to say, well, so suppose we just take non-relativistic quantum mechanics, we have x and p. Okay, we say that well, there are these variables x and p, and then they have a Poisson bracket such that this thing is 1, and then we raise this Poisson bracket to a commutator, x commutator p is I. We multiply Poisson brackets by I and make them true as commutator relations. Okay. But as you know from the study of classical mechanics, this structure of a commutator, the structure of a Poisson bracket, or even if you didn't know any of this, the structure of the Poisson bracket is a structure that is geometrical and is not tied to a particular set of variables, not tied to the set of variables x and p. Okay? You can use any variables in phase space and define a Poisson bracket, for these variables. Okay, so let's see more. What I mean. Look, so let's given a set of variables in phase space. Let's say that at the moment we're dealing with xi and pi's. J, so there's more than one x, more than one p now. Okay, let's say that this thing is omega ij. Okay, where omega ij is delta ij. Is delta ij, and we also have okay. So if we had a system of n x's and n p's, we've got a matrix, this omega matrix, which is 2n cross 2n dimensional, and it's an antisymmetric matrix. Okay? Now, if you want to move to more general variables than x's and p's, it's better to think of this omega as a tensor of the matrix. Okay? It's a tensor in both of whose indices are upper. Okay? Though, in order to do manipulations with it, I will find it more convenient to define the inverse of omega. Okay, this is a matrix, both of whose indices are lower. Okay, and to do my manipulations with that inverse of omega. That inverse of omega turns out to be the more geometrical object. Okay, so what is the inverse of omega? Well, once we've got omega, we can find its inverse. Okay, so if omega, remember xi pj, so writing xi and pj to say that it's the Poisson bracket with x on the left p, right, was equal to delta ij. It's easy to convince yourself that omega with a lower xi and pj is equal to minus delta ij. Now this is the fact that 0, 1 minus 1, 0 is the inverse of minus. In order to make it square root 1, you need to put a minus there. Make it a Pauli matrix. Okay? So, instead of dealing with this object here, this object which is an antisymmetric tensor on phase space, okay, I deal with this object here. Okay, now, whenever you have an antisymmetric tensor of any rank, but with lower indices, there is convenient notation to deal with this antisymmetric object that we're now going to use. Okay? This notation has a name, it makes it a form, but it's just notation. So, I'm going to encode these components, omega xi pj, into a geometrical object, which I'll call omega, which is omega xi pj, dxi, d, and then there's a symbol here, dpj. Okay? What does this mean? It's purely form. in order to understand what it means, it has the same formal content as the translation between the components of a metric and the expression for an infinitesimal distance. Right? So when you have a metric, you can characterize it by Gij. You can equally characterize it by a formula for the infinitesimal line element, which is a scalar object. ds squared is equal to Gij dxi dxj. Okay? So what I'm doing is taking this equivalent of a metric, which is the symplectic form, and multiplying it by some formal object. Okay? This thing here has an interpretation for sort of infinitesimal lengths. This thing is a formal object, and the only property of this formal object that we will use, is that it's antisymmetric. Because we're doing this for an antisymmetric object with lower emphasis, we encode the fact that this tensor is antisymmetric into a formal property of this D objects. Okay, so the formal property we will use is that dA wedge dt is equal to minus dt wedge dt. Later on in this course, maybe middle of next semester, we will return to a study of these geometrical ideas in much more detail. This not for use in quantization then, but use in study of compactification, space-time physics. Okay, so it's good to get used to this notation and these ideas anyway. We'll need them a lot later on. But at the moment, we don't want to go to systematic treatment. This is all I need about this object is that it's okay. Now, why have I told you all of this? I've told you all of this because there's a very nice way of thinking of the symplectic structure, the Poisson bracket structure of classical theory. You see, as we discussed in the previous class, a good sort of covariant way of thinking of phase space is to think of it as the class, okay, as the set of all classical solutions of the system. Okay, now an action induces a Poisson bracket structure, a symplectic form, on the space of solutions. If you label solutions by initial values of x and initial values of p, that symplectic structure is just delta p wedge delta x. It's not delta x wedge delta p, because remember this property. Once we lower, you pick up an additional minus. Okay? So if you use x and y to label solutions, the symplectic structure on that labeling of solutions is just delta x wedge delta p. But the symplectic form is a geometric object and can be expressed in any coordinates. So once you have a parametrization of phase space, if you want to know what the symplectic structure, what the Poisson bracket structure on this phase space is, what you have to do is to use canonical quantization to say that in the x and p parametrization, it's delta x wedge delta p with a minus sign, and then use the usual rules of tensor transformations to go to the symplectic form in any other system. Okay? Now this notation makes that particularly convenient, because if you've got a set of solutions explicitly, you know what xi is as a function of some parameters. You know what pi is for those solutions as a function of those parameters. In order to transform the symplectic form into form on these set of parameters, all you have to do is to put in what dx is in terms of d of those parameters. D transforms like a differential. You can easily check that that's like a differential element. That induces the right tensor transformation properties, omega. It's clear because the index is contracted. Okay? So all you have to do is to substitute what delta x is in terms of delta of the parameters of your solution, delta p is in terms of the parameters of your solution, and then you have the Poisson bracket structure in terms of the parameterization of your phase space, namely solution space, that is motion action. Okay? And then you can use that to invert this omega and find the Poisson brackets. Okay? On the space of on the objects that you will promote to operators that you like, not necessarily in terms of x and p. Is this clear? Now actually this procedure often leads you into a symplectic structure that's not flat. It's not like, In terms of new variables, you have constant functions times d something, d something. How to do the quantization then is a complicated and delicate story, which is the meat of geometric quantization, which we're not going to get in here because luckily in what we do at the moment, we'll always get flat symplectic spaces. So how to do the quantization will be great. Is this clear? Okay. So we're going to now implement this, use these ideas to quantize our space of solutions. Okay? The beauty of these ideas is that it uses when you can classically solve a system. You've done a lot of the work. This way of quantization uses the fact that you've correctly understood what the right space of classical solution is. Okay? In order to promote the theory to a quantitative. That's the situation we're in. We completely understand the classical theory. We should be able to relatively easily get quantitative theory out, but let's see how we do it. Is this clear? Okay, so let's move. So let's okay. We work in the gauge that we're working in. Okay, what was our action? Well, our action was 1 by 4 pi alpha, right? Integral d to sigma. Now okay, let's say even before fixing the gauge, that was g alpha beta del alpha is mu del alpha is mu and that's a minus. Okay. Now, in order to get the symplectic structure of space of solutions, what is the symplectic structure? Just for every variable, it's dx wedge dp. Summed over all variables. The variables are continuous, integrated over variables. Okay? So, what are the variables in the game? There's g alpha beta, and there are x views. What is the contribution to the symplectic structure from g alpha beta? Something. 0. It's 0 because the momentum conjugate to g alpha beta is 0. So that dp part is just 0. Okay, what's the contribution? Fine. So, you see, when we gauge fix, we must be careful to use the symplectic structure of the whole theory before sitting on the slice that we're interested in. Okay? But in this particular case, since we're fixing G something, G itself has no symplectic structure, we can just do the quantization on that slice. Okay, we've not missed anything. We've not missed any contribution to the symplectic structure. There you go. The next, okay. So what is the symplectic structure? Well, now we might as well switch to dots and primes. So the action as far as quantization is concerned is the same thing as d to sigma x mu. Okay. Now I'm going to split up into x plus dot, and this probably has a minus sign. X minus dot plus x plus prime x minus prime, and then plus xi dot squared minus xi prime squared. Let me check if I got signs right here. This one would be this is right because x plus is t plus x minus is t minus x. The part that comes from t and t should appear with minus sign. So that's correct. Okay, so this is our action. So what's the symplectic form that follows from this action? Okay, so the symplectic form that follows from this action is 1 by 4 pi, but now when we compute the momentum conjugate to any variable, okay, that's right, 1 by 4 pi alpha prime, then integral, now the momentum conjugate to x minus, okay, the momentum conjugate to x minus is minus x plus dot, okay, so we get minus x plus dot delta of this, that's delta is the same as d here. Okay, we are writing delta as a function. Okay, wedge delta of x minus. Okay, what's the momentum conjugate to x plus minus x minus dot? So plus, so minus delta of x minus dot wedge delta of x plus. Okay, and then plus sum over I 2 times delta of xi dot wedge delta of xi. Is this clear? Momentum conjugates to any variable times the variable. This is factor of 2 because momentum conjugate to xi as a 2. Delta is the same symbol as d. I'm using the symbol delta because it's a variation of a function, small variation of a function rather than small variation of a number. I could write d if you want. It's just a formula. It's the basis in space of one force. It doesn't matter. Just the basis behind which you write your omega. This has exactly the same information as the statement that the Poisson bracket between x minus and x plus dot is a delta function. That's all that is saying. It's standard canonical organization. X plus, it doesn't contribute to symplectic structure because symplectic structure is only derivative with momentum is derivative at the time. Okay, very good. Now, this is formally correct. However, we know what the right space of physical solutions is. Okay, so what is the correct space of physical solutions? The correct space of physical solutions, parameters label distinct physical solutions. Okay, or what? We can write xi as equal to, and I should write it the way I wrote it in my notes, and the way everyone writes it, it's an odd way to write it than standard. Xi is equal to x plus I, xi plus xi minus, where xi plus is equal to sum of alpha prime by 2, an arbitrary function of x plus, so that respects periodicities. Okay, so that's sum not n not equal to 0, alpha n divided by minus in e to the power minus I n plus, and then I should also write 0 mode computation, so that's xi0 plus alpha prime, where is alpha prime, pi done. And x minus I is equal to alpha prime by 2, sum n not equal to 0, alpha n tilde by minus in e to the power minus I. What have I done? Okay, I still have to write down some part connected with x plus and x minus. We'll do that in a moment. But here, what have I done? I've just taken an arbitrary function of xi and Fourier transformed it, added 0 matrices. The Fourier coefficients have been written with some strange prefactors, but that's my choice. It's a choice of conventions. I can redefine a new Fourier variable of, an is alpha n divided by minus in. This would just be standard Fourier. Is this clear? That these numbers alpha n tilde and x0i and pi plus 1, a couple of additional numbers that I will come have to do with the x plus x minus sector, give you a full labeling of all classical solutions. Of course, there are reality conditions here. Alpha n will have to be the complex conjugate of alpha minus n in order for this function to be real functions. So that we will keep that in mind. Is this clear? Okay, questions, comments. If you have any questions, comments, please stop me. If it's not clear to anyone, please say. The ideas are simple, but they may be answered. If anyone has questions like the other people have the same question, don't feel embarrassed.
So what happens to this x plus and x 1?
We can't do that. We've not yet done. Okay. But as we've seen before, this does not exhaust the space of solutions completely. Firstly, the constraint equations, as we saw last class, determine everything but the zero mode of x plus once we fix this gauge. Because it determines del plus of x plus and determines del minus of x plus, but it can tell you the zero mode. So that's what are the remaining. So what are the remaining parameters? So there's x plus, which is equal to something that's completely determined, and it will turn out, luckily, that we don't need to investigate its formula. Sorry. Hello. Listen, I'm teaching class. Sorry. Okay. So word plus there's a new parameter that's important because it parameterizes new solutions. That's an additional parameter in the space of solutions. The zero mode plus x minus is more rich. X minus has square root alpha prime t minus tau, which we sometimes like to think of as sigma plus plus sigma minus by 2. Okay, and then there's little x minus. So there are three new parameters. There are three additional numbers that parameterize solutions in the x plus x minus sum. Second, namely x0 plus, x0 minus, and field. It's where we get from solving the constraint in terms of all stars.
What is x0 plus?
X0 plus is the zero mode. Okay, that is undetermined by the constraint equations. The constraint equation only tells you about derivatives of x plus. So it's some constant based, no information. Okay, so yes, all of this is n not equal to 0. Alpha n tilde by minus in e to the power minus in sigma minus. Okay, now we want to determine the symplectic structure on the space of solutions. So all we have to do is to plug in these classical solutions into the symplectic form. Okay, but even before we start doing this in detail, and we will soon do it, but even before we start doing it in detail, we see something very nice. Because delta x minus. So what is delta? Delta is a variation as you move on the space of solutions. Okay? X minus has only one parameter or two parameters in which solutions change. X plus is much richer because this function is a function of all these alphas. So delta x plus is something very complicated. Okay? But basically because delta x minus is very simple. Delta x minus comes only from these parts. And these parts have no Fourier modes, as Fourier mode equal to 0. Okay? That immediately tells you that the only part of, and then using the fact that if you've got a constant function and you Fourier integrate it over from 0 to 2 pi, okay, a constant function multiplying another function, the only part of that function that's picked out is the 0 mode of that other function. You see that the only part that enters the symplectic form, the only part of x plus that enters the symplectic form is the 0 modes of x plus. Can you see that? Right. So, what do we have? Suppose we plug this space of solutions into the symplectic form. Okay? Let's look at this part of the symplectic form to start with. This delta x minus is what? It's delta p. Okay? So let's write it down. Let's write down the contribution from this term. Let's write down the contribution of this term, for instance. Okay, so we get delta of x dot plus let's write it down in this term. So delta of x dot minus where delta of x plus integrated. Now this integral includes an integral over sigma. What is delta of x dot minus? Okay, delta of x dot minus is simply alpha prime delta p minus. Because delta acts on the parameters in the linear solution space. Okay? And then we're waiting for delta of x plus. So while delta x plus is in general something very complicated, when once we do the integral, the only part of the x plus that survives is the zero mode part. Very probably Fourier transforms. Okay, so what we know about zero mode? Well, there's two pieces in the zero mode. Okay, there's the part that comes from here, and there's a part that comes from the time dependence, the p plus alpha prime p plus tau. Okay? Now, the part that comes from here will contribute very simply. It's just, it will have some delta of x0 plus. The part that comes from the time dependence is very complicated. It's very complicated because p plus is a very complicated function of all of this stuff. As we will see in a moment. You know, if you imagine doing the following. Solve for x plus. We have delta of x plus is equal to constant times delta xi. That's the constraint equation. Now look at the zero Fourier mode of that equation. That will give you p plus on the left hand side is equal to everything that has harmonic oscillator n with harmonic oscillator minus n from the quadratic term on the right hand side. So it's bilinear as an alpha, and that's very complicated. Is this clear? So all the complication in quantization, everything else is going to be very simple. Start from the i's are going to be very simple. But all the complication in quantization comes from the fact that p plus is a very complicated function of everything else. So if we actually have to plug this into the symplectic form, what p plus is a function of everything else, get a very complicated symplectic form, and it would look like that. Life would be very complicated, but we don't have to do that. Why is that? We don't have to do that because 3 is an odd number. Right. So let me say this more clearly. As we will see very soon, the variables here in the xi sector appear in canonical conjugate ways. You know, give us a nice structure of phase space. Okay. But so what we're left with is these three different numbers characterizing solutions. But you can't put a symplectic structure in an odd dimensional space. You can't put a non-degenerate symplectic structure in an odd dimensional space. You know this from Poisson brackets. Poisson brackets always come in pairs. If you have a third guy, it would have to be something in which the Poisson bracket, is zero. Another way of saying is that you take any antisymmetric matrix and it's odd, it's going to be degenerate, like a row of zeros. Okay? So it's a fundamental property that if you want to promote, you want to use some symplectic kind of structure and promote that to operate algebra, many consistency conditions must be created. One of which is that, the simplest of which is that you must be working in the even dimensional space. Okay. So, when you've got an odd dimensional phase space, you can't use this method of quantization unmodified. However, in this situation, the same thing is what Dirac used to call, this is an example of what Dirac used to call first class constraints. And it's a situation in which the second method that we've already seen in these lectures is justified. And the second method is the following. Let us forget about the fact that P plus is determined. Let's forget about the fact that P plus is determined by these constraints for a moment. And let's promote that to a dynamical level. So we'll say square root alpha prime P plus tau. And then do the quantization. So now we've got a new solution. So we've enlarged our phase space. How do we cure the fact that we've enlarged our phase space? Then we take the constraint that would have determined P plus and impose it as an operator equation. Okay? On our system. So that's the method we're going to follow. We're going to take this fictitiously, slightly enlarged class of solutions. Enlarge it one time. Okay? Do the quantization and impose the one non-trivial equation, the equation that would have determined P plus as a function of everything else, as an operator equation on Hilbert space. give us something reasonable.
Okay, we should have other modes also in X plus.
There are other modes in X plus, but those are completely solved for by the constraint. Better to say, they just don't enter the symplectic structure, as we've argued. Right? See, the space of solutions doesn't care about what those other modes are. The only way in which those other modes could affect the physical phase space is by contributing to the symplectic structure on physical phase space. But we see that it doesn't. It's only the zero mode part that can contribute. It's the zero mode we have to deal with here. Is this clear?
Shouldn't I be doing anything fishy by quantizing it with this extra p plus and then imposing?
Well, it's roughly as fishy as the kinds of things we did in quantum mechanics in the first class. You increase the number of variables and take constraints and impose them as operating functions. In the end, the test of a good quantization does it give you a consistent quantum theory? It has all the properties. We'll do a more systematic quantization, a path integral quantization, which is less ambiguous. We have a clear starting point, path integral. We'll do a more systematic quantization in the next few lectures, with the adequate formula theory. But at the moment, let's get the answer without such findings. Is this clear? As I said last class, it's very important as a research physicist to be able to do something rough and not completely something that won't necessarily satisfy a mathematician, but get the answer fast. Because that way you see whether something interesting is happening. If something interesting comes out, then you spend a lot of time understanding it. But if it's not going to be interesting, why bother? So it's very important to do rough investigation before being very thorough. Okay, good. So now let's complete our quantization. So what we're going to do is to take this class of solutions with this symplectic form, this class of solutions with this symplectic form, and do the quantization imposing that one or rather two ways, this 1 to the x plus sector, 1 to the x minus sector, remaining constraints. Okay, so let's first do the quantization and then quantify the constraints. Okay, so let's first deal with the xi sector. So the xi sectors we've plugged in like this. Now we have to plug that into the symplectic. Okay, so what do we get? Okay, let's first deal with the zero modes of xi. The zero modes of xi are very simple. What we want to do is to plug the zero mode expansion into 1 by 2 alpha. Okay, 1 by 2 pi alpha prime. But now you do the integral over sigma, that gives you a factor of 2 pi. So sorry, 1 by 4 pi alpha, right? Then you do the integral over sigma, and that gives you a factor of 2 pi. So that's 1 by 2 alpha prime times integral of there's a 2 here, so that gives that. And then we have integral of delta of alpha prime pi, which delta of x0. Is this clear? See, what I'm doing is that we've got a quadratic expression which only gives you something non-zero if a mode n meets mode minus n in sigma. So the zero modes can only click with themselves. So I'm isolating out the contribution of the zero modes first. Is this clear? Okay, I've just taken this expansion, plugged it in here, and seen what I get from zero modes. Okay, when I do x dot, I don't get anything from x0. Okay? And I'm doing it at tau equals 0, so at tau equals 0, this thing is 0 unless I take a time derivative. Is this clear? Okay? So, oh sorry, did I have square root alpha? I had put square root alpha primes and properties. This expansion should have been without square roots, I'm sorry about that. Should be basically chosen to cancel this alpha prime, yeah? This is not square root. Okay, so this is simply delta pi wedge delta x0y. This is the standard px commutation relationship for quantum mechanics. Is this clear? So the quantization of the zero-mode sector is very simple. The Hilbert space square integrable functions of x0y and momentum is implemented by the differential operator. This is the we landed up to the zero modes, the same problem as ordinary quantum mechanics. Is this clear? Okay. Now, what about the x plus x minus vector? The x plus x minus vectors all zero modes. Okay. So if I wanted to, I could move back to the coordinates x0 and x1, and then the quantization of the zero modes is exact for each of these things is exactly like any of the xi's. So I don't need to say anything new about the quantization of these coordinates. It's exactly the same as this. Is this clear? So we quantize all the zero modes. What we've landed up with is functions of d variables. Okay, with the differential operators being implemented as parameters.
We haven't written on the zero modes which arise from n.
You see, what we're trying to do is write a symplectic structure on zero modes. Okay, that will contribute to the symplectic structure on alpha ends. We're doing that. But our x0 and the p enter into the symplectic structure only in this form. We've completely determined that. The quantization of that sector is clear. It's decoupled, right? The zero modes don't talk to the other things. So we've got one Hilbert space that is just functions of d variables, square integrable functions of d variables. Is this clear? Okay. Now, what about the rest? So let's move to that.
All the d variables?
At the moment, it's all the d variables. You see, because we've got x0s and p's for all d variables.
Right, but
we haven't imposed a constraint yet. That will knock things down. But before imposing the constraint, it's all d variables. This is completely analogous to our second method of quantizing the particle. Remember, we had functions of all d variables, and then there was some constraint that gave you a partial range. This is going to be an exact analogy. Okay, in fact, this quantization of the zero mode is that. It's the same thing. Okay, now let's return to the non-zero modes. Okay, the non-zero modes are quantized very simply. By using the same procedure. So let's plug in to this object and see what we get. Okay, now we've got a 2 and a 4 pi, so that becomes a 2 pi. Then when we do an integral, we get a factor of 2 pi when momenta click. Okay, so we'll have 1 by alpha prime. But the way we've written our expansion, there's an explicit factor of square root alpha prime behind each of the oscillators. Everything is quadratic, so the alpha primes will cancel. We've also got a factor of 2, so all that we're left with is a half. So we've got half, and then whatever else comes from here. Okay, so whatever else comes from here, remember we absorb this 2 also. So half times delta of xi dot wedge delta of where we've done the integral over sigma. Is that notation? Fine, let me try. Delta. Half times what? It comes from here. We only get contributions when momenta are equal. Okay, so let's first take delta. Delta is delta alpha. It's just plugging in here. Okay, so when we plug in here, what we get delta. When we take dot, this factor has been chosen exactly to cancel what we get by differentiating. Okay? So the dot part is delta alpha n e to the power minus I n sigma plus delta alpha n tilde e to the power minus I n sigma minus wedge And then there's apart from delta x, not delta x dot, this term, yeah? Okay, wedge, okay, let me be more systematic. Let me add 1 by 4 pi, and I've not yet done the integral. This is sigma, d sigma. Wedge delta alpha n divided by minus in is by minus in sigma plus delta alpha n tilde minus in is by minus in sigma minus x. Okay, really there's a summation over n here, summation over n here, summation over m here. Some different variable m, and there's the integral.
Tau equal to 0, both sigma plus and sigma minus will become basically sigma.
Basically sigma, but there's a minus sign.
No.
Yes, so sigma plus and sigma minus are sigma and minus. Okay, so let's make that explanation. Sigma plus is sigma, and sigma minus is minus sigma. Now that we've taken the time derivative, we can just make the replacement. Okay, sigma plus. This was plus and this was minus. Okay, so this is sigma plus is sigma. I am sigma, and it had a minus, and this is plus I am sigma. Okay, sorry for the unsystematic nature of this thing, but if anything is unclear, please ask. The summation goes over n and n. But the summation, because of the integral, we get a click only when the Fourier modes add up to 0. Okay? So there are two kinds of terms. There are the terms in which you have alpha with alpha, and the terms, or alpha tilde with alpha tilde, or the terms in which you have alpha with alpha tilde and alpha tilde with alpha. Now the first thing to notice is that the terms between alpha and alpha tilde add up to 0. Because you have, okay, so it only clicks when n is equal to m, and then you get delta alpha n wedge delta alpha tilde n plus delta alpha tilde n wedge delta alpha n, both divided by minus I. Is this clear? The two ends are the same, so we don't have to worry about which n you're putting in the denominator.
Sorry, I think why you are taking the tau goes to 0 thing.
Well, quantization is done on a constant time slice.
Right.
It doesn't matter which time.
So you're choosing that to be
You're choosing it to be time. You can check that symplectic form is invariant under time translations. So it doesn't matter. Because of the antisymmetry, this is just it. Is this clear? So we forget about the terms which have alpha with alpha tilde, alpha tilde. Okay. Now, you might think, well, is the other set of terms also going to give us 0 because of antisymmetry? But it's not. Okay, I'm clear in this. It's not going to give us 0 because here we get non-zero clicks between alpha at n and alpha at minus n. Okay, because n plus n has to be equal to 0. Okay, so let's write down what we get. We get 1 by 4 pi, then delta alpha n wedge delta alpha minus n. Okay, now the 4 pi has become 1 by 2 because of the 2 pi that we get from the integral over sigma. So 1 by 2 delta alpha n by delta alpha minus n and divided by minus I of m, but m was minus n. So plus in. Right? This is summed over n, and we get the same thing with the other terms. Now this n is summed over all non-zero values. Okay, but when you take minus the contribution from, let's say, look at the contribution from n equals 20 and n equals minus 20. These two contributions add instead of subtracting, because the denominator changes sign, and you get a sign change when you flip the positions. Okay, the key point was clicking was between n and minus n instead of n and n. Okay, and therefore this thing can be written as n is equal to 1 to infinity of delta alpha n divided wedge delta alpha minus n divided by in plus delta alpha tilde n wedge delta alpha tilde minus n divided by in. Okay, so quantization of this sector is now also totally trivial. You say you've got a bunch of terms, each of which is quadratically decoupled from everything else. Alpha n talks to alpha minus n. I should also have been putting an I in x everywhere. I'll do it now. So dealing with any one scalar, all the xi's. Okay, I should have been putting that. I just put it at the end. Okay, now what is the correct quantization of the symplectic form? Well, we know that if we had delta something wedge delta something, that is the commutator. The second with the first has commutator I. Okay, this is telling us what omega is with lower indices. So omega with lower indices has an additional factor of I n in the denominator. Therefore, omega with upper indices has an additional factor of I n in the numerator. Okay? So we conclude that this with this has a commutation relation of x and p times I n. Okay? Therefore we conclude that alpha minus ni, commutator alpha ni, is equal to I times I n. Okay? Or alpha n I, commutator alpha minus n, have reverse positions to get a minus sign, is equal to n. Okay? In fact, if I made this more general, of course there's only commutators between alphas with the same n, so I can write this more, or alphas with the same I. So I can write this more generally as delta n delta ij. That completes our quantization. We've got to implement the we've got a Hilbert space with these alphas that have this combination. Now, what does this combination relate to mean? This is basically harmonic oscillator creation operator, annihilation operator, creation operator with frequency n. Right? So, the remaining part of our Hilbert space is a bunch of harmonic oscillators with frequency that goes from 1, 2, 3, 4 up to infinity. Okay, 1, 2, 3, 4 up to infinity. And there are d minus 2 copies of these. Actually, d minus 2 times 2 copies of these, because although I have not mentioned it, everything that we do for the alphas also holds for the alpha tildes. Is this clear? Okay? So we've got d minus 2 times 2 sequences of harmonic oscillators with frequencies 1 to infinity. So each of these Hilbert spaces tensor with each other, tensor with the Hilbert space of functions, square integrable functions of D variables. That is the full Hilbert space that we get from quantization. Is this clear? Okay, now I want to go on to an analysis of the constraint, but I don't want to do that until I get some feedback from you. Has this been clear? Okay, let me do the analysis of the constraint, then we come back. Okay, so I want to say 2-3 things. I've used slightly fancy techniques to do the quantization here. The techniques were fancy, and the reason I use these slightly fancy techniques, but first it's much faster than standard techniques. And second, the logic for this way of proceeding is much clearer when said in this language. However, what I have done in content is exactly the same as the following. Start from the action we wrote down right at the end of last class. That is an action for 0 modes all coordinates and oscillators for d minus 2 coordinates, and do the quantization of the system any way you want. Just do the standard thing that Peskin-Schroeder does, for instance. For quantization of 1 plus 1 dimensional field thing. However you do it, you get this answer. So anyone who is in both cases we've not yet dealt with the constraint. Last time I also secretly enlarged the Hilbert space a little bit without us seeing what was going on. This is much clearer because we see what was going on. Okay, but anyway, so what I want to say is that the quantization we've done so far is exactly the same as what you get if you start with the action we wrote down right at the end of last class. In 0 modes for all coordinates, oscillators for d minus 2, and did the quantization any way you want. Parameterize configuration space in some set of variables, find the conjugate momentum, turn these into harmonic oscillators in every way you want to do it. You'll find that it's exactly the same thing as this. Okay, this is just a little faster. Okay? Anyone who feels uncomfortable with the way we, with all these delta this and symplectic forms and I don't know all this stuff, just take that action we started with the end of last class. This is a very useful exercise, strongly recommended. Use your favorite method of canonical quantization and find the answer. You'll get this answer. Okay? Please do that if you feel uncomfortable. It's not necessary to be jazzy, except for the logic, where it's much clearer this way. Okay, that is the first point. Now, that was the only one. The thing we want to do now is to impose the constraint. Okay. So, what was the constraint? So the constraint was the equation del plus x mu equals 0. And a similar one with minus. So let's deal with the plus constraint. So, what do we get from the 0 mode part of this constraint? You see, the 0 mode part of the constraint, you remember what x mu was. X mu was equal to x0 mu, that clearly does the constraint equation, plus alpha prime p mu into sigma plus sigma minus by 2. Okay, plus oscillator. Plus, in fact, let's write it oscillators. The oscillator part is only accurate for the i's, but it's alpha prime by 2, and then alpha n by minus in e to the power minus I n. Okay, where this part is correct only if we put about the i's. You understand that, right? Don't need the first two terms for x0 or x1. Okay, so let's evaluate this constraint. Let's first see what the 0 modes give us. Okay, So what do we get from 0 modes? So from the 0 modes we get the only contribution to the 0 modes is plus hits sigma plus. So we just get alpha prime p mu by 4. By 4 because tau was sigma plus sigma minus by 2. We get 2 factors of by 2. Is this clear? Okay? I should have said that of course we are only interested in that part of this constraint equation is a function equation. It's a function of sigma. But as we've seen before, we are only interested in the part of the constraint that's 0 mode in sigma. Okay? So we are only interested in the 0 frequency Fourier component of this. So we're interested in the integral of this constraint over sigma. Because everything else relates oscillators are sigma plus. Okay, to the coordinates of interest in oscillators, sigma plus are just nominal quantization. We don't care about that. It's true, but we don't care. X plus. Yeah, X plus. Okay? So the only term in X plus that is in our quantization is P plus. That is the term that's going to get constrained. Okay? So the only term in the constraint equation that's of interest to us, that's not relating something outside what we are interested in, okay, is the 0 mode of the constraint. The integral of that constraint over sigma. Okay? And that's what I'm evaluating. I'm just taking the path that is no Fourier mode, no Fourier frequency. Okay. What are we going to get from this other stuff? Okay. From well, from the other stuff, what do we get? I'm getting powers of alpha prime wrong, which is silly. Okay, let's. Oh, this alpha prime squared. Okay, two factors of alpha prime in a moment. So yeah, expansion alpha prime being not squared. And now from the 0 mode part, what do we get? From the oscillators, what do we get? Well, we get alpha prime by 2 because we've got something squared. And then we get sigma you see, now when we take the del plus of this, these ions vanish. So we just get sigma alpha ni alpha minus ni. Some alpha is n equal to n is not equal to 0. This is the only 0 frequency part of that constraint. Okay? Great. Now we're nearly through. Sorry?
The contributions from X plus and
X plus, this, yes. Now, all that is involved there is letting this mu run over all this. Because the 0 mode part of X plus X minus is the same. Okay? So let's just say that this is summed only over I equals 1 to d minus 2, but this is summed over X.
Okay, two questions. The X minus doesn't have any mode. I feel like it just has
oscillators. Yes.
It doesn't have any oscillator.
Yes.
But X plus has oscillator modes which can in principle give a contribution like this.
Well, the X plus oscillator modes are determined by the constraint equations in terms of everything else.
Yes.
So they're not labels on phase space. The space of solution is completely determined by what the oscillator modes of the d minus 2.
Yes.
Okay? That is a complete characterization of the space of solutions. Now the only way in which the fact that X plus does oscillate, and it does, the only way in which that could affect our quantization is in contributing to the symplectic form in terms of the other variables. You see, X plus, apart from 0 modes, is determined, what X plus is doing is determined by what the other degrees of freedom are doing. So there are no new degrees of freedom associated with X plus. It's just a question of whether that stuff flapping around affects the symplectic form for the labels of our solutions or not. Okay? And we've gone through this argument to demonstrate that it doesn't. Well, it does in a certain way from this P class business, but we're taking that into account by imposing a constraint. It's the only way to do it. Good. Please keep asking. This is very important. It's very important.
Okay, it's not clear to me why X plus oscillator. Okay, let's say we have an oscillator mode which would be like alpha plus.
Yes. It's there and it's a it can be. It's some function.
It will be from alpha plus to the power in minus alpha plus.
Where alpha plus is given by a bilinear function of alpha n i's.
Yeah, that's all.
Okay.
But so now how do we now that? But that function,
yes,
will enter here.
No, enter okay. Not in the zero mode of the constraint. You see, we're taking this constraint and integrating over sigma.
Yes.
So anything with non-zero frequency drops out. Right? It would be non-zero frequency because x minus has only zero frequency.
Okay. That's because if one of them is x plus, another is x plus.
Exactly. If one is x plus, the other is x plus. Good. Okay. Fine. So let's go. So let's understand what this thing is. See, we've got the summation over all n. Okay? But the summation over all n can includes both n positive and n negative. Now when n negative is to the right, we've got the creation operators to the right. Remember we saw that alpha n with n positive was like destruction, like the A's. Okay? When n positive is to the right, we've got the destruction operations to the right. Now it's always a good idea to write things in normal order form. So let's do that. So we've got the equation 0 is equal to alpha prime squared p mu by 4 plus